Hello and welcome to the International Postdoc Forum for the Philosophy of Science, hosted by the Minnesota Center for Philosophy of Science. My name is Alan Love, and I'm the director of the Minnesota Center for Philosophy of Science. And I am delighted today to introduce Sarita Rosenstock, who will be our guest for the day. Sarita is coming to us from the Australian National University and therefore is actually delivering this presentation on Saturday morning. And we are excited that she could join us. She has been at Australian National University since 2019. She finished her PhD at the University of California, Irvine in the Logic and Philosophy of Science program. And her dissertation was entitled A Categorical Consideration of Physical Formalisms. She's published a number of papers, recently accepted and now forthcoming, Learning from the Shape of Data to Appear in Philosophy of Science. A couple years back, In Epistemic Networks is Less Really More, with a couple co-authors also in Philosophy of Science. And she's also done work in Philosophy of Physics, a paper from 2016 on Einstein algebras and relativistic spacetimes. Today, the focus of her presentation will be, and I just need to switch my own window here that got out of whack, is a category-theoretic framework for physical representation. And just as a reminder, there will be a commentary after Sarita's presentation by Sam Fletcher, and I will introduce Sam after Sarita's talk finishes. And I will stop my own introduction now and turn the floor over to Sarita. Sarita, please, a category-theoretic framework for physical representation.
Hi, everybody. Thanks for coming. So today I'm going to talk to you about how category theory, which we can think of as the mathematical theory of structure, can help us articulate how we use mathematical formalisms to represent physical systems. I'm starting from what I think is a pretty modest assumption that you're always going to have to make some arbitrary decisions when you represent something in a particular way, but that doesn't make your representations meaningless. So electromagnetism is going to be the same theory, whether I say it in English or Spanish, whatever symbols or fonts I use. And these notational choices can cut even deeper too, like whether I write Maxwell's equations using integrals or derivatives, or whether I have a symbol at all for my magnetic field or just define it in terms of my electric field. But the boundaries between content and description are not always clear or agreed upon, and are sometimes themselves the subject matter of scientific inquiry. So today I'm going to start by telling two stories that I think illustrate this, and I'll be referring back to them throughout the talk. So once upon a time, this guy Galileo dreamed of a man trapped in the hull of a ship with no windows. And Galileo wondered whether there was any means by which this man could determine if the ship was at rest or moving at a constant speed. And he argued that there was no experiment that the man could perform from within the ship to distinguish between rest and constant motion. And he concluded that, by analogy, a proper theory of mechanics shouldn't distinguish between states of affairs in which everything in the entire universe, our own inescapable ship, is moving at a constant speed or at rest. But Newton disagreed for his own idiosyncratic reasons. And he came up with a really great universal theory of mechanics, one that builds in exactly the kind of privileged rest frame that Galileo didn't think made any sense to articulate. So Newton's framework was widely adopted and fruitfully employed, even by people who didn't think the rest frame was meaningful. And here I want to ask whether, by conceiving of Newton's formalism from a Galilean perspective, we're magically transforming the same symbols into a different formal framework. That is, have we actually created a new framework simply by thinking of these changes in rest frame as not physically meaningful? And if that's allowed, and you need to know how I feel about a formalism to know what it means, then you can't really ever fully articulate what you mean by a formalism, can you? And instead of answering these questions, I'm going to tell you another story. Okay, so since at least as far back as Aristotle, there have been philosophical debates about the nature of existence that can be described as relationism versus substantivalism. Substantivalists think that there's a thing out there that's space, or space-time as we now think of it, whereas relationists think that's a bit ontologically presumptuous, since all we really have evidence for is things in space, or space-time, and relations between them. Then one day, this guy, Albert Einstein, comes along, and he hands us this really great theory called general relativity, which does away with some of the really conspicuous substancy stuff, like ether. But it still involves this thing called a space-time manifold, which still looks a little too much like a space-time substance for some dedicated relationists, like John Ehrman. So Ehrman looks long and hard, and he finds a mathematical object that mathematician Bob Garrosh came up with, which Ehrman calls an Einstein algebra. And Einstein algebras seem to do everything that we want general relativity to do, but without positing a space-time manifold. Instead, they merely present possible relations among possible configurations of matter in an abstract way. And Ehrman wants to declare victory for relationists once and for all in light of this new formalism. But we're left with the question: is the space-time manifold really gone? That is this new formalism really offering a genuinely new alternative to the old way of describing general relativity, one that lacks an ontological commitment to the space-time manifold? And the questions posed in both of these examples have just the right form for us to apply what I'm calling the theories as categories of models approach in response, which myself and a number of other philosophers of physics have used. We start with some question of the form: do two theoretical formalisms have the same content as one another, or does one involve stronger ontological commitments than the other? We then do some mysterious category theory magic and conclude that the physically relevant relationship between the two formalisms is that one of them has more or less or the same amount of what we call structure, properties, or stuff than the other, or else we conclude that they're incommensurable. And the basic idea that I want to get across in this talk is that when we use this framework, it gives us a scaffold to tell a story about the relationships among these formalisms and between those formalisms in the world that's constrained to be consistent with how we use them to represent things. So here are the things that I want to talk to you about today. First off, I really need to finally tell you what a category is, and I'll tell you everything that you need to know about category theory in order to start applying this theories as categories of models methodology to compare different physical formalisms. I'll then go into some more detail about how I think mathematical formalisms represent physical systems and why category theory captures this idea. And then I'll turn back to the stories yet again to show how including that representational context can give us a more motivated way of using this category theoretic methodology. Okay. So what we're trying to accomplish by introducing category theory is to give a precise account of what we mean by a particular theoretical formalism. We could just describe it in words, but we want to make sure we're getting at the real language-independent content. So instead, what we do is we lay out all of the ways that we can use that formalism to represent a physical system, all of the different models of the world that theory lets us define. This is the first step in defining a category. The next step is realizing that we're missing some information here. In particular, we're missing information about which aspects of the models are supposed to be physically meaningful. For example, if my theory uses squares like these to represent systems, does it matter what color a square is or what size? We can't know these things by just looking at the collection of models. And so we add in some more information about the relationships between models. In the simplest case, and for the purpose of my talk, we just talk about isomorphisms, which tell us when two models are supposed to describe the same physical situation. You can also add more sophisticated arrows in, like system-subsystem relations. And in this way, we can be increasingly precise about how these abstract formal things can and can't be used to represent physical systems. And that's all a category is. It's a bunch of objects, which for us right now, we're thinking of as formal mathematical objects that can represent physical systems, but in general can be anything at all. And a bunch of arrows between those objects, which again, can be interpreted in all sorts of ways. But for this, we're thinking of them as relationships between mathematical models, and especially relationships of equivalence or isomorphism. And the only constraints are that every object has an identity arrow, and that you can compose arrows, string them together to make new arrows. And now the way that you can compare two categories is using what's called a functor. A functor takes objects to objects and arrows to arrows in such a way as preserves the identity arrows and compositions of arrows. So more than just telling us which model in the first formalism corresponds to which model in the second, a functor will also tell us how relationships among the models translate between the formalisms. And now you have enough background for me to give you some more detail about how the mysterious math is going to work. So again, we begin with the question of the form. Do two theoretical formalisms, T1 and T2, say the same thing about the content of a physical system, or does one of them involve stronger ontological commitments than another? And answering this question involves a step-by-step process along the lines of saying that formalism 1 can be understood as category C1, formalism 2 can be understood as category C2. The relationship between these two formalisms can be understood as a functor between these two categories, or else that the relationship is not functorial, in which case the theories are structurally incomparable. We then observe some properties of this functor, which I'll explain in a moment. And from this, we infer that the physically relevant relationship between the two formalisms is that one of them has more or less or the same amount of what we call structure, properties, or stuff as the other. So the next thing I'm going to do for you right now is tell you which properties of functors we'll be looking at. And then I'm going to explain how these properties line up with the structure, properties, stuff in the formalisms. And after that, I'm going to be a bit more specific about what this can be understood as relation is supposed to be. Okay. The first property of functors is fullness. A functor is full if for any two objects in the first category. If we restrict the functor to just the maps between the first object and the second, and we look at the arrows between the objects that the functor maps them to, then every one of these new arrows has a preimage in the first category. For us, this means that when we look at any two models in our initial physical formalism, we know that the functor isn't going to add in any new relations between the objects when we move over into the new formalism. A functor is faithful if no two arrows on the left are mapped to the same arrow on the right. And this is going to ensure that all of the relations between models in our initial formalism are represented still when we use the functor to translate over into the new formalism. And finally, our functor is essentially surjective if every object in the second category is isomorphic to one in the image of the functor. So I don't need a one-to-one correspondence between models in my first formalism and models in my new formalism. It's okay here, for example, that there's nothing in the first category that maps to this red object because it's isomorphic to the green object, which does have a representative in the first category. And these properties let us tell a story about the relationship between physical formalisms that these categories stand for. If a functor is full, faithful, and essentially surjective, then it realizes what's called an equivalence of categories, which we're going to interpret as a kind of theoretical equivalence. And if the functor fails to be either full, faithful, or essentially surjective, then it's forgetting some feature of the initial category in the move to the image. We can use these three properties of functors to help us figure out what exactly is being forgotten. Now these labels, properties, structure, and stuff, they come from an email exchange in the late 90s between a mathematician, John Baez, and his graduate students. They were playing around with the idea that what they called mathematical gadgets, which was a catch-all for anything that mathematicians refer to in the course of theorizing, can be thought of as being built up by starting from what they call stuff, such as a set or a space, the most basic substrate that you want to take for granted when you're defining your gadget, and that this stuff can be equipped with extra structure, like subsets, elements, or relations, which satisfy certain properties, like equations, inequalities, or inclusions. And that's all pretty abstract, so let's look at an example. Let's take the concept of a function to be our gadget. We can think of a function as a pair of sets, x and y, the domain and the range, equipped with a particular subset of pairs of elements from x and y, a structure. And now This structured stuff has to satisfy the further property that for every element of the domain X, there's a unique element of the range Y that's paired with that element in the set F. And this property is what makes it a function as opposed to any old relation. And I should note that this decomposition is almost never going to be unique. You can usually carve up a gadget in a few different ways, depending on what you want to think of as the essential stuff and what you think of as more of as elaborations on that stuff. But by associating the components of the gadget with the properties of a functor, we circumvent this problem by only ever talking about relative property structure and stuff as expressed by the functor. And so now I'm going to go through some examples to show how this property structure stuff story lines up with our category theoretic definitions. So for our first category, we'll just have one object, the square, and our arrows are symmetries of the square. So transformations that preserve its squareness. That's going to mean rotations and multiples of 90 degrees, reflections over the horizontal, the vertical, and the diagonal axes. For our second category, we have this other square, which appears to have some additional structure that distinguishes its sides from its top and bottom. Its symmetries are 180-degree rotation and horizontal and vertical reflection. We can then define a pretty natural functor from the second category to the first, which acts as the identity on arrows. And since there's only one object in both categories, it's obviously essentially surjective. And since it acts as the identity on arrows, it's going to be faithful. But it's not full, since not all symmetries of the square are symmetries of the square with orange sides. So this functor forgets only structure, and we can think of the structure that it's forgetting as the structure of its lateral sides. And so from the way that the functor was defined, we can see the lateral sides are being treated as an additional structure on top of the square stuff in light of this functor. Now here's an example of forgetting stuff. We'll still look at our old square category, but we'll also consider this third category, square star star, where I've tacked on an additional square that can move independently of the outside square. So my arrows here will be all of the same arrows from my regular square paired with all the different symmetries of the inside square. And again, there's a pretty natural functor I can define that relates these two gadgets. I can take an arrow from my double square and just ignore what's happening to the inside square. And again, this functor is essentially surjective since there's only one object in each category. So it doesn't forget properties. But this time it's full. Every symmetry of the square corresponds to at least one symmetry of the double square. So it doesn't forget structure. But it isn't faithful since lots of symmetries of the double square correspond to the same symmetry of the outside square. So it forgets stuff. And we can think of the stuff that it forgets as the purple square. And here's an example where we forget properties. I've defined a fourth category of colored squares, which has two extra objects corresponding to different colors of squares. I have arrows in this category corresponding to symmetries of each of these squares. This time, my functor goes from the square category to the colored square category. It takes my one square to the green square on the right. And the functor is full and faithful since the green square has all of the same arrows in both categories. But it's not essentially surjective. None of the other colored squares are represented in the first category. So it forgets properties, and we can think of the property that it forgets is that of being green as opposed to any other color. And in this last example, I'll show you an equivalence. So everything is the same as in the last example, but now I've added arrows between each of the colored squares. So in this new category, not only can I rotate and reflect my squares, I can also recolor them. And as before, the functor is full and faithful, but now it's also essentially surjective because each of the objects in my right category are isomorphic to an object that's hit by the functor, namely the green square. And the idea here is that by adding these recoloring arrows to my colored square category, I've signaled that the colors of the squares don't have any intrinsic representational significance. Anytime I use a red square to represent something, I could have just as easily used a blue square. So these extra colors don't actually give me any more of a capacity to represent anything as I had before. It's only by removing those recoloring arrows that I signal to you that you should care about the color. Now, this classification scheme doesn't always latch on in a straightforward way to our intuitive notions of properties, structure, and stuff. But in general, they tend to work like this. Forgetting properties corresponds to expanding the scope, like going from looking at just the green squares to looking at squares of different colors, or from looking at temporally oriented spacetimes to spacetimes that may or may not permit time travel. Forgetting stuff corresponds to reducing dimension, like going from 2 independently moving squares to just one of them, or from looking at spacetime with an electromagnetic field on it to just the underlying spacetime. And forgetting structure corresponds to adding noise or eliminating artifacts, depending on how you look at it. For example, when I forget about the structure of the absolute rest frame from Newton's perspective, I'm obscuring an important distinction between the universe at rest and the universe moving at a constant velocity. But for relationists, I'm eliminating an artifact of my representation and revealing the more essential representational parts of my gadget. So let's have another look at that example from this new perspective. On the left, I've defined a category gal. The objects of gal are just formal descriptions of spacetimes, and the arrows are all of the ways that I can transform the spacetime formalism without obtaining a distinct physical possibility. So, for example, I can shift everything to the left, I can rotate it, I can set it all to move at a constant velocity. But I can't, for example, add new people because that would be a distinct physical possibility. And on the right, I've defined another category, newt. And this time, the objects are, again, just formal descriptions of spacetimes, but now they have to include a specification of whether objects are at rest. These arrows include many of the same transformations that I had in the Galilean case, but only the ones that preserve the rest frame. And we can then define a functor from newt to gal that takes spacetimes to spacetimes and transformations to transformations, since every Newtonian transformation is also a Galilean transformation, but not vice versa. And we can interpret this functor as forgetting the rest frame as it moves from the Newtonian category to the Galilean category, in a way that corresponds to how we think about Newtonian spacetimes as being Galilean spacetimes plus the extra structure of a rest frame. And similarly, we can define a category associated with the manifold formalism for general relativity. And this is going to have manifolds with an additional structure called a metric, which essentially tells us how gravity will act on matter if we add some in. And its arrows will be diffeomorphisms, which are the structure preserving maps for manifolds, which also preserve the metric. And for Einstein algebras, we have these new gadgets as objects and their associated structure preserving maps as arrows. And in a paper with some colleagues of mine, we showed that what we take to be the natural functor between these two categories turns out to be an equivalence. And in that paper, we interpret this categorical equivalence as demonstrating that there's no difference in the content of these formalisms. And therefore, that expressing general relativity in terms of Einstein algebras doesn't actually eliminate the space-time manifold like Ehrman hoped it would. It just makes it implicit rather than explicit in the presentation of the theory. And so if you care about what a formal model really says about what's in the world in a way that's independent of the particular way that you've expressed that content in words or symbols, then the theory of Einstein algebras tells us all of the same things about what exists and what doesn't exist as the formulation of general relativity that uses manifolds with metrics, at least according to us in that paper. But there's a problem. Why should you take our word for it? That is there a principled reason why you should choose one category over another to represent a formalism, or one functor over another to represent a relationship between formalisms? And this is a point where my view tends to diverge from my colleagues who also employ category theory in a similar way to what I've described here. My answer is basically, yes, these choices are somewhat arbitrary, but that doesn't make them unprincipled. And in particular, while our categories and functors aren't going to fall from heaven, I'm going to argue that there is a sense in which they do fall out of a clear articulation of how we're using our formalisms to represent stuff. So now I'm going to take a little detour to explain how I'm understanding representation here. So let's say you want to use some mathematical gadget to represent some states of affairs in the world. I'm not a philosopher of language, but I'm pretty sure that the way language works is if I point to a gadget and say this thing, it can be anything, a word, a picture, a sentence, a mathematical model, and I want you to connect it with some way that the world can be, then we both have to have an understanding that I could have chosen a different object instead to denote a different state of affairs. And the considerations that led us to talk about category theory in the first place also apply here. We don't just have a collection of alternate representations, because some changes I might make to my gadget, like writing in a different font, don't have any physical meaning. So it makes sense to include some relations between representations, and that makes it a category. And similarly, there are probably lots of ways that the world could be different from the state that I'm referring to that I don't really care about. And so I can think of states of affairs as a category as well. And I don't have to have any particular association between representations and states of affairs in mind. There could be a few choices that you, who I'm trying to communicate with, can make that are going to be consistent with the representational story that I'm trying to tell. And I'm calling this thing that I just built here a representation diagram. It's a specification of the range of representations I might have used and the states of affairs they could represent, along with the acceptable ways to tie those together. And I don't mean for this to be a positive definition of what representation means, but I think that whatever it is that you do think you're doing when you assume a representational relationship, it's possible to at least approximately characterize it in these terms. So here's a more concrete example. Let's say I'm planning an event and I've asked you to help me set things up by handing you this seating chart. And this figure has a lot of features that I could alter to populate the space of possible representations. I can move it to the left. I can add more squares. I can add some triangles. I never really have to stop. I can similarly invoke as fine-grained picture as I want of the room where I want you to set this all up. But the conventions about communication and about event planning and physical restrictions on how chairs work are going to immediately reduce the scope of possibilities. It seems pretty clear, for example, that I mean for you to associate each square with a single chair, so I'm telling you that there should be 12 chairs as opposed to 11 or 50, and moreover that these should probably be arranged in 3 neat rows of 4 chairs each. But there is some room for reasonable people to disagree about some of the other aspects of representation, like whether we should attribute any significance to the spacing between the chairs. And depending on the room, there might be more than one orientation of the chairs that would make sense. This might lead you to ask me for more clarification as to the nature of the representational relationship that I'm presuming, or you might take my lack of specificity as a signal that any number of those interpretations that you might choose are equally acceptable. And so to reiterate, the basic idea here is that for a gadget to represent a state of affairs, both the gadget and the state have to be drawn from some, perhaps ill-specified, space of alternatives, and there has to be at least one way we can understand them to hook up to one another. Now, I don't claim that all acts of representation can be formalized as representation diagrams. I actually think that most acts of representations can't be straightforwardly interpreted in this way. But largely that's because I think most acts of representations are vague and ill-specified. And considering the various ways that an event planner might use the diagram I showed you to indicate a spatial arrangement, it's kind of impressive that successful communication can nonetheless occur between humans. But it can also break down, and these breakdowns can often be explained by failures of precision in the act of representation. And I think the same thing is true for scientists. It's often sufficient that a mathematical gadget serves its intended purpose. It's only when problems arise, or when one asks theoretical questions about possible extensions or variations of the theory, that it becomes important to be more precise about how the representation is supposed to work. And you can do that by defining a representation diagram like this. Okay, now this is the fun part. Once you have a representation diagram, you can use it to define a unique category, what I'm calling the structure category, to stand in for the formal theory when applying the theories as categories of models framework. And I'm not going to go into too many details here, but one of the cool things about category theory is that it lets you give functional definitions of lots of gadgets that are familiar from mathematics, but in a very general way as objects in a category that bear a certain kind of relationship with other objects. You can describe these relationships that you're intending using what's called a universal property. And you can use that to construct the unique thing that satisfies that property. And in this case, if we start with a representation diagram, we can define the structure category as the unique up to categorical equivalence category that serves to mediate the relationship between the representation category and the states of affairs category as that relationship is expressed by the interpretation functors. In other words, every interpretation of representations as states of affairs can be decomposed into a fixed functor, which I'm calling the Occam functor, that translates representations into this new structure category, and an interpretation of these new representations as states of affairs. And you could think of the structure category as a more parsimonious representation category, or a more parsimonious states of affairs category, which we get by throwing out all of the features of these categories that aren't relevant to our interpretations. And this shows how we can justify a particular choice of category, the structure category, on the basis of how we use the formalism as we've encoded it in our representation diagram. And we can also use this representational framework to justify the choice of a particular functor for comparing formalisms. So let's say I have two formalisms that I'm encoding as these two representation diagrams. In order to compare these, I'm going to need some additional cues as to how they're supposed to relate. And that might be a way of connecting the representation diagrams or the states of affairs categories, or one of the states of affairs categories to the other representation category. And this too is ultimately going to be rooted in some story we're telling about how these formalisms relate. And it had better be one that's consistent with how these frameworks are actually used, which is going to mean that it also has to appropriately relate to the interpretation functors. So let's see how this can be brought to bear on our examples. In our first example, we can think of both of the frameworks as using the same representational source, which we get from Newton, but thinking of it as relating to the world in two different ways. For Newton, it's going to matter that the rest frame in the formalism maps to a rest frame in the world. But Galileo doesn't think there is such a thing as a rest frame in the world, so his interpretations don't need to worry about that. And we can think of these different interpretations as giving us new structure categories, which we can think of as Gal and Newt. And the category-theoretic features of these structure categories are going to induce a unique functorial relationship, which we can think of as forgetting the structure of absolute rest in the move from Newtonian structure to Galilean structure. Now, this process looks a bit different for our second story. Here, there is no real representational framework that's associated with Einstein algebras at all. Instead, what we have first is a mathematical relationship between manifolds with metric and Einstein algebras, which we get from Bob Garish. And from John Ehrman, we get a proposal for using this relationship to construct a representational framework for general relativity using these new gadgets. But the only empirically sensible way to do that is to mediate through the manifold framework, which is where we get all of our observational validation for general relativity. And again, the category-theoretic features of our structure categories are going to induce a unique functorial relationship. And in this case, it turns out to be an equivalence. And right now I should confess that this construction using representation diagrams, this is just a post hoc justification for the choice of categories and functors in that paper. So in practice, the representation diagram framework served as more of a metaphorical role in the construction of the categories and functor. So considerations about how the manifold framework is used in general relativity served as justifications for the choices of which transformations count as isomorphisms in our manifold category. And considerations about how Einstein algebras are representationally mediated through the manifold framework helped us hone in on what the Einstein algebra isomorphisms had to be and what the functorial relationship was between these two categories. But I still think it's a useful metaphor and one that does capture the thought process that went into that paper. And another thing I should confess here is that I don't actually think that this equivalence verdict is the end of the story about the relationship between these formalisms. This equivalence shows that they technically have the same semantic content, sure, but theoretical frameworks are so much more than their truth conditions. A large part of what made the first formalism so powerful is the visibility of centering the manifold with metric. And when we look at things this way, we're more likely to ask questions like, what if we were to extend space-time here or stretch it there? And there's a real sense in which many of the developments in space-time physics would not have been feasible without giving the space-time manifold a name. And conversely, Einstein algebras seem to be more readily conducive to quantization. And the way I see it, acknowledging the formal equivalence between these frameworks frees us to take full advantage of these different pragmatic capacities without worrying about which one is more true. And so to summarize, I introduced a theories as categories of models methodology as a way of providing a scaffold for telling a story about the relationships between physical formalisms that's constrained to be consistent with how we use them. By defining the categories, we're just pinning down a particular characterization of the semantic content of a formalism so we can subject it to formal analysis. And by defining a functor, we're telling a story about the relationship between the formalisms. And then the property structure stuff heuristic just summarizes that story, which we can then give a stronger formal validation to by invoking representation diagrams. And that's my talk. Thanks for listening.
Thank you, Sarita, for that admirably clear and succinct presentation. Now we have the opportunity for a commentary from my colleague, Sam Fletcher, who is an assistant professor, soon to be associate professor in the Department of Philosophy here at the University of Minnesota and resident fellow of the Minnesota Center for Philosophy of Science. He's also an external member of the Munich Center for Mathematical Philosophy and currently the McKnight Land Grant Professor here at the University of Minnesota. Sam, I'm going to turn the floor over to you now for your commentary, please.
Great. Thank you, Alan, and thank you especially, Sarita. I think that one of the things that Sarita's presentation brings to the fore is that we have tools that are so expressive for trying to capture many sorts of different relationships that philosophers of science have been interested in when it comes to scientific models and representations. Even though the examples are typically, or have typically so far been drawn from the physical sciences, they're generally applicable. And they generally concern the relationships between how we ought to understand our models and the things that they represent. I just have a few comments and ideas that I had while reading Sarita's work that I thought might be fruitful to engender some discussion. So I have a couple of comments, first of all, on the representation diagrams and the Occam functors. And then I also have a couple of comments on the property structure stuff distinction that Sarita began her talk with. So let's start with the representation diagrams and the Occam functors. So this is what a representation diagram is or looks like. We've got a category. That's the stuff that's doing the representing. We've got a bunch of these maps. These are, you can think of them as different functions that take elements in this category to elements in this category and relationships of sameness, isomorphism, in this category to relationships in this category. And the stuff in this category is what's being represented. So we've got the stuff doing the representing, the stuff represented, and in the middle, these are the ways or the admissible collection of ways to represent. So if one thinks about representation as a kind of human act, it's the postulation of this particular class of maps between two particular categories that is the act of representation. There's some similarities here, I think, with some things that we see, for example, in Ron Geary's approaches to understanding the nature of scientific theories. So in his 1988 book, Explaining Science, a Cognitive Approach, he understands scientific theories as models plus statements about how or what the models represent. You might call them theoretical hypotheses. So the stuff here are the scientific models. The hypotheses, the statements about what and how they represent, are these ones here. Now, it does raise this question about what the state of affairs are supposed to be, the things that are represented. They could be possible things in the world, but oftentimes, if we were applying this approach, this category here could be more models. In fact, when we go to analyze how different representational frameworks describe states of affairs, we won't often think about it in terms of the states of affairs themselves. but in terms of themselves models of those states of affairs. These could be ways the world could be. They could be as well merely classes of empirical predictions or possible observations. It's important to note that oftentimes we only know about or can describe the states of affairs that we're interested in through our representation category. Oftentimes, we don't start with these two separately and think about how to represent the one or the other. Oftentimes, we'll have an idea about what we want to represent that's vague, that allows us to construct this. And then by specifying a collection of ways to represent, it allows us to specify what the states of affairs are. So we shouldn't think of the picture that we get from Sarita's presentation as one where we have to start off separately with knowledge about the states of affairs and knowledge about possible representations of them, and then make a decision about how we want to use the one to represent the other. Oftentimes, pragmatically, the one may be constructed in the process of articulating the other. Another thing, though, is that we need to have some sorts of restrictions on the admissible interpretations. If the admissible interpretations are arbitrary, then it's well, here's another way of putting things. When it's arbitrary, there's very little we can conclude, very few conclusions we can draw without any further restrictions. And this is a generic feature of that I mentioned at the beginning of category theory's expressive power. When there are very few restrictions on something, there are many ways that things could be. There's very little we can conclude in general about them. I think that if we're using category theory in this manner to understand how scientific representation works, we should try to think of restrictions on these classes of representations that more accurately describe assumptions that we do actually make when we're thinking about representation. So here's an example of one thing you might do. Here I've got a category theory diagram involving representations, some states of affairs. This is a particular choice of one of our admissible representations. This SD here is the structure category that Sarita was talking about. And FD here is the Occam functor. There is a certain sense in which what this does is it looks at classes of states of affairs that are related by different possible representations to one another. Now, one assumption that one could make, which is expressed in technical language here, but can be expressed pretty simply as the idea that if two ways of representing states of affairs have overlapping representational capacities, that is to say that the stuff that they can represent overlaps with one another, then the two classes of representational capacities, the things that they can represent, are in fact the same as one another. The idea of this assumption is that one partitions the different ways that models in this representation category can represent states of affairs into cells or classes. If one does so, then what the structure category has as its objects and has as its arrows between them are the sets of the representational capacities of the objects in rep and the arrows in rep. So if we do make some further assumptions, we can connect this idea of a structure category and this idea of an Occam functor to this idea of representational capacities more closely. That raises the question about whether or not Occam functors should be called rather representational capacity functors, and whether structure categories should be called representation categories. It's not that we're not discarding unnecessary ontological commitments, but we're actually as Occam would, right? But rather we're summarizing what the representational commitments in fact are. Okay, a little bit more on property, structure, and stuff. So one of the things we saw is this division between different relative amounts of stuff, structure, and properties based on the nature of certain types of functors between different categories. Now, this language, more or less stuff, more or less structure, more or less properties, suggests some sort of at least ordering on stuff, structure, and properties between categories. But in order for these comparisons to be meaningful for scientific representation, it needs to be that the stuff, the structure, and the properties in the categories are actually things that are playing some important representational role. So, and in general, unless we put further restrictions on the framework, that won't necessarily be the case. In the first place, this more stuff than, or more structure than, or more properties than relation may not be a partial order. It may not actually even be irreflexive or asymmetric. So normally we think that if A has more than B and B has more than C, then A has more than C, for instance. That won't necessarily be the case. So good. Let's see here. What exactly has more stuff or structure or properties? Do we compare the representation categories? Do we compare the state of affairs categories? Do we compare somehow the representation diagrams themselves? I'm inclined towards this sort of answer because it involves both the models and the things that they're representing. So let me give you an example of how I think that might work. It involves having a common point of comparison between two representation diagrams. Here I've got two representation diagrams along with their appropriate structure categories that have the same state of affairs. Now, in this particular situation, we can imagine one described as Sarita did, that this first category here is the class of Galilean spacetime models, and this one here is the class of Newtonian spacetime models. So the main difference between them is that the Newtonian ones have a standard of absolute rest. They have a notion of true rest, and the Galilean ones don't. Then we can consider two sorts of cases. If the states of affairs really represented are the Newtonian worlds, then we can have arrows, functors between the different structure categories that make the diagram commute, but both of which forget various sorts of structure properties, one in one direction and then in the other. How do we interpret such a situation? Well, we can do so by reference to the state of affairs. We would say that Rep2, which here is the Newtonian models, represent more finely the Newtonian states of affairs. But we can only do so in comparison with what the SOA category is. Conversely, if the state of affairs are Galilean spacetime models, then these two categories are actually going to be equivalent with one another. But then we would say Rep1 represents less superfluously than Rep2. Rep2 adds in a standard of rest that is something that we don't think exists in our state of affairs. So I think that if we want to use the property structure stuff distinction in combination with representation diagrams and what Sarita has called structure categories, we'll need to think not just about comparing the structure categories, but the whole relationship between different structure categories, different representation categories, and possibly different states of affairs categories. I hope that considering these sorts of relationships will produce a richer conception of the different types of relationships that about representation that can be modeled in this categorical framework.
Okay, thank you, Sam. With that, I'm going to ask Sarita to come back onto the screen. And Sarita is going to have an opportunity to respond to Sam's comments. But while she is doing that, I wanted to very quickly alert people that if you have a question, please do use the raise hand function at the bottom of your screen. That will alert me that you have a question, and I can get to you in the order that you ask. If for some reason you would not like to ask your question in person, but would rather type it in the chat, please simply do that, and then I will read out the question for Sarita to respond to. We've got plenty of time for questions, so I would encourage you definitely to ask what comes to mind. But first, let's start with giving Sarita an opportunity to respond to Sam. Sarita.
Hi, yes, thank you so much, Sam. That was really helpful. So I have a couple of notes of points that you made that I think are worth highlighting. So the first thing that you said, that you mentioned, is, I think, a really important point, which is that it's not really clear what the states of affairs category is supposed to be, but it is, I am conceiving of it here as itself a category of representations and not like things in the world, which to my more metaphysically inclined colleagues tends to make it seem like I'm doing some sort of like idealist thing where I have an idea. I'm sort of moving it down a level and not really clarifying anything. But for me, I was really just trying to capture this idea that I don't usually think of the practice of science as trying to exactly reflect what's in the world. And so I think that the considerations about, like, you're trying to tell a story about a sort of simplified picture of what's happening. And you have an understanding that there are things in the world that could be different where your model still applies. And you have an understanding that there are things in your representations that could be different and your model still applies. And I think sometimes conceptually it helps to separate those things, like in order to have a better picture of how you're using the representation. But another thing that's happening with the states of affairs category here is that I'm taking advantage of one of the cool features of category theory, is which it kind of lets you black box what the objects are. So I can just think of the states of affairs category as arbitrarily fine-grained, but I don't have to actually know what's in them. I can say, well, there's some collection of states of affairs, and whatever else is the case, if I have a transformation, and if I have two states of affairs and they only differ by something that I think is trivial, like, I don't know, my hair is a little longer, then there's going to be an isomorphism between them. So I can characterize that without actually looking into what I think the objects actually are. A second point which is well taken, is that I should really be adding some restrictions on what counts as admissible interpretations. And I was kind of trying to avoid that in the paper that this talk is based on, with the idea that if I write out my representation diagram and it turns out that what I think are my admissible interpretations lead to some weird conclusions, then that's an iterative process where I go back and try to write it better so it seems to better capture what I mean. But I think that there's probably going to be something interesting you can say at the end of that kind of process about what does and doesn't count as a good set of interpretation functors. There's also the point about the nomenclature that I'm using when I call it the Occam functor, which is also a really good point, which is, in talking about the structure category, in the way that I'm doing, I'm explicitly trying to I don't want to identify things that are treated the same by the theory necessarily. I want to keep the sort of rhetorical power of being able to separate them and have that isomorphism visible. And so because of that, I'm not sort of throwing everything away. I'm just trying to just be a little bit more succinct about what I mean, but sort of still like have my cake and eat it too, hold on to everything. So I'm not going all the way in terms of just getting rid of distinctions and getting the most simple thing I can possibly have. I'm trying to still let myself see those distinctions, but recognize them for what they are. And the last point that Sam made about how the sort of your verdict on the relationship between the formalisms is going to depend on sort of your starting perspective on what you think states of affairs actually are. That's also a really good point. Like, and that's one where that's one of the ways in which this doesn't really resolve disputes about relative structure. It just structures them, right? So it's showing essentially that like if I am thinking of everything as sort of you're standing in the context of a theory, and then you're asking from this context of this theory, if I were to translate over into another theory, what's happening? Am I preserving everything I'm doing? Am I losing something? Am I adding something? But yeah, it's always going to be perspectival in that way, which I think is really interesting. But yeah, it does mean that it's not going to be a resolution. It's just going to be a bit of a scaffold. Right. Those are my initial reactions to Sam's.
Great. Thank you, Sarita. So we will keep you front and center here as we have the question and answer. Sam, did you want to follow up a little bit on any of the points that Sarita responded to?
I could. There's a lot of things that we could talk about, but maybe I'll just pick out one. So let's riff on this last comment that you made, Sarita, now applied to the case that you, Jim Weatherall and Thomas Barrett worked on, that you described in your presentation about the relationship between Lorentzian manifolds, the standard objects for describing relativistic spacetimes, the models of general relativity, and these Einstein algebras. Mm-hmm. So if we want to say that we've got a functor between these two that realizes an equivalence, if we want to then say more than this is just a formal statement about the relationships between two classes of mathematical gadgets, we also want to say something about what these two things are representing, right? So if we have a common point of comparison, if we think that they're representing the same states of affairs, then we can show how the different pieces of the gadgets represents the same stuff. But if the question is whether or not they could be representing different states of affairs, then it seems that if we wanted to resolve that question, which I take it what like the original question was, right? So Ehrman thought, here is a formalism which is evocative of a more relational way of understanding general relativity. He would imagine it like that the states of affairs being described are not, it's not a category with manifolds, it's something else, right? And so if it is something else, is that something else can it also be represented by the standard space-time manifolds, right? And if so, does the categorical equivalence between the manifolds and the Einstein algebras preserve those representational relationships? So I'm not sure if I'm being precise enough in describing the idea, but it seems that like in the example, right, there's got to be some reference. There's got to be some reference to the states of affairs these two formalisms are representing, if we want to say that they're not just equivalent formalisms, but they are theoretically equivalent as scientific theories.
Yeah, that's a really good point. I think that so it sounds a little bit question begging that if we start from a perspective of we're thinking of them as we're kind of agreeing with Ehrman that we think that maybe transposition, like diffeomorphisms aren't going to be of the space-time manifold aren't going to be physically meaningful, then, and that's how we're thinking of the space-time category, then the sort of thing follows that they're the same because we're treating that category like that. But there's a couple of things that are going on here. One of them is that we had to, like, it wasn't a given from where our starting place that you can define an Einstein algebra from a manifold that you could go back without losing information. And so that was sort of a discovery about the particular nature of that formalism. So it's true that like the mathematical structure of that formalism, regardless of how you're interpreting it, is going to constrain the ways in which you could interpret it. And so that's one way of saying it, is saying that actually formally you can do the same things in both of these places. And what that's going to mean essentially is that if you try to rephrase like Ehrman's point in this context, what you would say is like, he would want to say that we have our representations and we have our states of affairs. We're taking it for granted that we're not being substantival here. And so that's not a property of the states of affairs. And in this one place, I have these space-time manifolds that I don't really need because there's nothing in the world that corresponds to them. And here I don't. And what we're basically saying is it's not really true, in the sense that because you have this equivalence between the formalisms prior to interpretation, you can define uniquely a manifold given an Einstein algebra. And it's going to be a clunky definition, but it's going to be there. And once you have that there, you can have preserving that being an additional condition, like an additional on your admissible interpretations, which is going to get you the other story, which is that they're both substantival. Right. So it's not so yeah, in this case too, it's going to depend on your perspective, but so this is more of a pre-interpretation sort of verdict about that, is that like the condition of the manifold has meaning is something that you can express them in both ways and you get the same answer.
Right. I guess I have in mind a sort of example where if one is mathematically sufficiently clever, one can take, say, like a category that represents one-dimensional vector spaces, right? And through clever constructions, one can construct a category that has two-dimensional vector spaces. And the way that one does that is just like very clever manipulations of constructions of the real numbers, right? And you can imagine on these appropriate constructions, we've got these two categories that you can use to realize a very particular functor, a very, very particular functor that realizes an equivalence between them.
Yeah.
Now, as a formal matter, that's neat. But if you think that the vector spaces were like representing like space or something like that, you're like, no. These are not, they may be equivalent according to this functor as formalisms, but they're not equivalent as theories of space. And the way that you would do that is you would say that these functors, they don't preserve some sort of like empirical information about how the different things are representing. And this is where I see those, your collection of representation diagrams to a common state of affairs playing a role in articulating that. Yeah,
that's right. So this is a lot of my colleagues who work on the same thing want to solve the problem that you described there by saying that if you have enough conditions on your functor, that can describe the relationship between the categories, then the existence of a functor satisfying those conditions is enough to demonstrate the property structure stuff relationship. Whereas I want to say, right, like, and so you want to have some way to have conditions that preclude that. And for me, I want those conditions to be essentially, that's not going to work if how you're thinking of these things as representing is not compatible with that functor. So if you draw out the diagram, you can't sort of, it's not going to commute. And so that's a little bit, it's going to be less restrictive. It still might be pluralist in the sorts of comparisons that are allowed. But right, I don't think that there's going to be a way of saying once and for all, because this functor exists, this is a relationship between the formalisms.
Okay, that is very helpful, and I appreciate Sam's engagement with Sarita on that. Are there any questions that any of our audience would like to ask Sarita? Well, maybe while giving people time to think about whether they have a question, I will ask one. So I think that one of the things, as somebody less familiar with this specific area, I am thinking of when you are going through it is that there are a number of choices that are being made in the analysis that depend on prior commitments. So at a couple of points, you mentioned kind of the metaphysical commitments that somebody might have. And then also you've highlighted particular epistemological commitments, maybe say with respect to whether or not you would be a pluralist, say, in what you admit in these choices. And so I think just from my sort of limited perspective, I would be curious to hear you say a little bit about how you think some of the debates that are going on, some of which you are engaging here, but more broadly even than what you've talked about today, kind of really trace back to some of these other commitments people have prior to the deployment of the formal category theory machinery. And so the disagreements are sort of elsewhere in the space. And I take it that some of what you were just talking about with Sam is in that space, because you're highlighting about the degree to which how some people want to solve the problem this way, as opposed to your own preference for solving it a different way. Of course, those are not decisions that category theory itself determines, but rather some other kinds of commitments in the background. So I'd be curious to hear you speak a little bit to how you see some of those commitments driving some of these debates that people are having about representation and category theory.
Yeah, those are some really good points there. So I think maybe a place to start is that I think when people talk about formalism representing a system, there's like people often will want to say something will want to sort of take it for granted that you can sort of look at the formalism and see how it's supposed to map on, that just saying it represents is kind of enough to know what it's representing. And then you can look at the formalism and the fact that it represents will let you look at the formalism and see what's there. And I'm sort of simultaneously rejecting that and trying my best to reconstruct it. So I'm saying basically you can't know what by looking at the formalism how it latches to the world, but maybe if you are specify it enough, you can get something closer to that, which will actually let you read the content out more or less to some extent, right? So, or rather, insofar as you can read the content, it's restricting the sorts of things that could be said of the world. So if I have two descriptions that I think are both valid descriptions of a system, and something is true in one and false in the other, then that can't hold of the system while I simultaneously hold those beliefs. And so that's basically what I'm saying is that I'm trying to clarify the sense in which you can and can't read off of a formalism what's in the world by restricting the sort of domain of the sorts of things that you could say about the world, given the various ways that you could say it. Right. And so the other thing is essentially, right. So what I think that some of my colleagues want to do is they want to be able to say, we have these formalisms. Let's assume that we've articulated them right. What if we were able to say definitively, if we can find a functor that satisfies such and such conditions, then that functor will tell us once and for all the relationship. And I just don't see that as the sort of thing, I don't see that as the place where category theory is actually useful here. Where I see it as useful more is providing a sort of platform for like finding common ground, like seeing if you can formulate your perspective in some sort of shared framework that will let you see the implied kind of relationship and work through it there, but it's not going to resolve those questions at all. It's just going to maybe maybe clarify them, maybe capture them in a shared framework.
So yeah, so that sounds like a different expectation for what the category theory is going to do for you, and that some of your interlocutors are sort of maybe investing much more highly in what category theory will deliver in terms of something like a definitive answer about the representation question, whereas I'm hearing you highlight that the category theory serves as a sort of toolkit that lets you probe and explore. But if you're expecting it to somehow spit out an answer like, say, a vending machine or something like that, just punch the right buttons and category theory will tell me, that's probably not what you think we should be expecting in these discussions about representation.
Yeah, that's a great way to put it. And maybe I should clarify that so it's less that my colleagues think that it is going to deliver this sort of magical verdict, but that they either feel like they need to defend it against accusations that it can't, or that that the fact that it might not be able to is actually a sort of counts against it.
Yeah.
And I just sort of want to sidestep that.
Good. So we've got a question in the chat. Let me try and articulate it. So it asks, what theories does the categorical approach that Sarita is offering and applied to the two examples in the paper, how could that be applicable to other domains besides the say Newtonian, Galilean motion example and the Einsteinian example that you went through?
Yeah, that's so right. I included the Newton Galileo thing not so as more familiar as an example of one where we already kind of know what history decided about the relationship as a sort of sanity check. And I included the Einstein algebra one as something where sort of a teaser for how it can deliver sort of maybe a new kind, like help us understand things going forward. So maybe I guess I can talk about something I'm working on right now that uses this.
Sounds like a good idea.
So right now I'm thinking about clustering algorithms in data analysis and thinking about the relationship between conceptualizing data as a metric space. So you have data points and you have distance between them, and conceptualizing it as sort of as clusters, so partitions of the data that are sort of trying to tell you what things are more similar to one another than to the rest of the data set. And you're obviously always going to lose some information when you do that. But the structure of how you're representing the data is going to constrain the sorts of like valid ways of turning that data into like a scheme for making clusters. And it's going to sort of let you in some situations characterize all of the valid ways of doing that, which I think is really cool. So that's the sort of thing where that can serve a purpose of you're given a data set, you want to know, like you're trying to find like, is there a clear way of talking about like natural kinds in this data set? Like, was it revealing like clusters in the world that I should care about? And what I want to say here is that you can, like, if you clarify what you care about and how you're conceiving of the content of the data, to an extent, you can do that with some caveats by expressing it in this way.
Yeah, so I think that's a really helpful answer to that question, because it points out that the kind of theoretical context that you might be working with could be quite thin in some of these data sets that you want to represent compared to some of these other situations where we might have a richer starting theoretical framework to be thinking about in the sense of the physical theory in particular, not the category theory. Okay, so follow-up question in the chat. So this applies beyond physics, great, but staying with physics, I was wondering whether this applies to dualities. I don't know if that is enough information to answer that, Sarita.
So
does that make sense as a question?
Yeah, so this is going to depend on what you mean by duality. Category theoretically, actually, what I'm calling an equivalence between Einstein algebras and general relativity is a category theoretic duality in the sense that it actually flips the arrows when it moves. And so depending, so there is a, so in that sense, I'm not exactly sure what you mean by duality here, but I think actually my advisor and co-author Jim Weatherall has something on dualities in physics on this topic as well. And I'm not sure, there's some relationship between the category theoretic and the physics notion, but I'm not totally clear on it.
Clarification in the chat from the question. By dualities, I meant the ADS-CFT correspondence. And
I think that is one of the examples that Jim talks about in his paper on that. So that would be worth looking at. I'm not myself very familiar with that theoretical framework.
Okay. So, but obviously the point is that it connects. And so there's work on that. Yep. Great. Other questions or comments that people have for Sarita?
Do you mind if I ask another question?
No, go ahead, Sam.
Yeah, I was hoping we could just like riff a little bit on like what kinds of ways we think in certain circumstances would be reasonable to constrain the admissible interpretations. Like we don't have to give a once and for all answer about anything, but about everything. But like I think it'd be good to like brainstorm a bit about that. So I gave one example, right, where in that example, if you've got two representation functors, these little I things, that have overlapping representational capacities, then in fact the representational capacities are the same. This is supposed to express somehow the idea that if you've got two models that can represent the same thing, the same state of affairs, they can do so in virtue of the facts of some particular fact about what they are in their native category. So if they both have this, if they both can represent that one thing together, then the idea goes, anything else that they can represent, they ought to be able to do so equally. Now, there's nothing required actually, like technically, in how things have been set up to have that sort of constraint. But the nice thing about that is that it really allows you to like give a very nice interpretation of what the objects and the arrows in the structure category are, right? The objects are just the collection of states of affairs that can be represented by the same models. And similarly with the arrows. Another idea that I've argued for in print is that if you have two objects that are isomorphic in a category, then they ought to have the same representational capacities. So admissible interpretations are going to be ones that respect the isomorphisms in the representation category. And if we have an arbitrary collection, right, of representation functors, that may not be the case. Anyway, these are just some ideas, and I don't think this is this complete story about what's going on. But I'm just curious about what you think about these sorts of examples, or if you have any other sorts of ideas.
Yeah, so this is like actually a great starting point. So I should first mention that I think that, so the restriction that isomorphic things map to isomorphic things, that's going to be a restriction already on the functor.
It's not that they...
Right, so
sorry.
Yeah.
It's not that they map to isomorphic things. They may map to non-isomorphic things, but the collection of things that they map to.
Yeah, so that's great. So I think that the lines that you're thinking on are sort of where I would like to go with that too, which is essentially that the restrictions that you would add are some sort of closure properties. Like you would say, well, I've indicated that I can use this and this for the same thing. So, and I can use also this and this for the same thing. So that should probably maybe be transitive. Or like if I can use a blue square or a green square to represent something, then I'm not necessarily signaling that I can use any color, but I'm signaling that you should sort of look at the color switches that are allowed and kind of close, like algebraically close the set of admissible interpretations in some way, if that makes sense. And so that would include things like isomorphism. Yeah.
Yeah.
Okay.
Yeah, but so like having the isomorphism thing would be basically saying if I have a functor, then any sort of naturally equivalent functor is also going to be there.
Oh, that's very interesting.
Yeah.
Okay, I'm going to go to one last question in the chat, and I will read it, and then Sarita, you can build off of it from what you can understand given what's here. From my very basic understanding of this, it sounds like the category theory works backwards. To clarify, I might be misunderstanding it as creating connections based off of two separate frameworks. But in that case, wouldn't you be able to create these connections with enough finesse with any framework? I feel like I'm misunderstanding this a bit and would like some clarification.
Yeah, no, I don't think you're misunderstanding it. I think that one of the things that, insofar as category theory is a tool, what it does is it tells you the kind of finessing you need to do to make a story work. So if you want to say these two things are related in a certain way, but you try to say it and it's not actually a functor, or it is a functor, but you kind of wanted them to be equivalent or they weren't, then you can look back and say, okay, either you either accept that, or you say, no, I actually care more about the relationship than the particular way I've written it down. So let's play around with what the functor was or what the categories were in order to make it work. And that's both part of the process of saying, of figuring out, for example, what you've forgotten. You say, like, how do I change these categories to turn it into an equivalence? That's going to help you see what you've forgotten. But it might also help you see what you meant in the first place, depending on how you're using it. So it is kind of a tool that lets you sort of finesse around the corners to say whatever you want, but make sure that you're saying it in a sort of globally consistent way. And there's also the thing going on here where like you can think of like what something means as as sort of characterized by all of the different transformations that preserve it, or you can think of all of the transformations that preserve something as like in terms of what it means, right? Like, and so you can kind of go back and forth, and I think that methodologically you usually will.
Okay, and we have a thank you in the chat, and they had one quick follow-up, basically like trying to create a language between these separate frameworks.
Yeah, exactly. And so if you're able to come up with a functor, that's what you've essentially done, and kind of the amount of contortion you have to do in order to do that is an indication of just how kind of far apart they were in the first place.
Okay, great. Thank you, Sarita, for wonderful discussion, answering a number of different questions, and really appreciate your presentation, stimulating that for us today. I wanted to briefly remind everyone as we close that about a month from now, we will have our next International Postdoc Forum from Rune de Rup from the University of Cambridge, who will be talking about pursuit worthiness, inductive risk, and female Viking warriors. You can find out more about that by going to the Minnesota Center for Philosophy of Science website. And with that, I will close us for today and say thank you and hope everyone has a great weekend. Take care.